I've been discussing a lot with Vladhead to take what he's been doing with the planetary disks and try to sort of generalize it a little bit, add a few more source terms and stuff, and maybe use it for galactic evolution, because that's one of the things I'm working with. Now, usually when you do galactic evolution models, you tend to forget about the internal dynamics, which is, of course, wrong, basically. And for one thing, and that's what I'm most interested in, is that you have gas flows, internal gas flows in the disk, can, in some cases, have large effects on, say, the nuclear synthetic evolution and so on. So the main objective was to do galaxy evolution, gas raises power. That may or may not be a good assumption, but since we don't, it's hard to model the details, and if you want to make a global model of galaxy disk, you can't do the details of star formation as well. That's just impossible. In the beginning, it's an insanely big computational project. And then we had to take into account the stellar lifetimes, the gas return from stars. They first consume that gas as they form and then return gas as they evolve. And nuclear synthesis and stuff like that, which is then just prescribed in the sense that you have a huge grid of numbers that you plug in, basically, taken from stellar evolution models. So, what should actually be computed in this case? What's the actual simulation? Well, there's the gas flows, stellar dynamics, possible magnetic fields, which is something I'm not going to be concerned with to begin with, and the various rates, like star formation rate, supernova rate, gas return rates, and so on. These are the things that we're interested in computing. And to have a look at the equations then. These are the equations for mass conservation as they will look if you do the galaxy evolution. I mean, the basic thing here is that the total mass density is equal to the rate of infall. The change of the total mass is equal to the rate of infall. And then you have term for the density of stars, then you have the density of the gas, and so on, and perhaps for certain given elements, an element I here. I'll have to look. Now, as you can see here, the continuity equation does have some source terms now. And one of the most problematic ones is this one, of course. Because that's not a natural source term in the equation. And that might cause a problem in, oh sorry, I should say one more thing. In equation 2 here, we have another source term which is really important, and that's the gas ejection source term. I mean, gas being returned from stars as they evolve, then that's another source term in the case. And this source term turns out to be a rather ugly integral equation. Now, it's ugly when you try to attack it analytically. Fortunately, it's very nice when you attack it by numerical integration. So, it would be, I think, possible to add a routine to Pencil where you actually compute this rate as you go along with the evolution and compute hydrodynamics and so on.
This you're thinking in 3D or disk?
3D or 2D. It depends. I mean, I guess if you want to run long simulation, I think 2D is a necessary assumption due to computing time, basically. But,
one thing which happens to real galaxies is the star formation exceeds certain thresholds. They're rejecting stuff.
Wind. Yeah, I know. I'll get back to that. And that's a problem when you run 2D models. I know that. You're then just pushing the sides that may not be accurate. But that's also something which, if you have
you could put another loss term in your
exactly. or you can assume that the wind is very small, which is usually the case for the big galaxy with deep potential. So, and there's no significant loss. I mean, you may puff up the disk, but the material will fall back again.
Not necessarily.
Not necessarily, but
simply.
No, I don't know that's the problem. But anyway, this is sort of one of the terms you need to add. You may possibly do approximations like instantaneous recycling, which means you assume that the stars return their gas at the same instant as they're being formed. This works pretty well in many cases, but I'm not sure it's going to work in this case, but that could be one of the things to try out. Then the conservation of momentum and energy would look different as well. I know this is not the way you guys seem to write the equations when you work with pencil. I don't know why, but anyway. Again, we have more source terms. We have, for instance, gravity source term, which includes the halo potential. This means also you have to add the self-gravity of the disk, but as like we heard earlier on, the self-gravity is no longer a problem in pencil, right? Or should work. And then you have this ejection term, you have star formation, and you have the infall term, which is probably the greatest problem, I think.
I mean, at least self-gravity works with periodic boundary.
Only periodic boundary condition.
But maybe one can assume it. And infinite number of galaxies lying next to each other.
Yeah. Okay. I don't know. The thing is that probably at the outer rim, so to speak, the density will go to zero somehow. So maybe you can use that to construct some artificial boundary condition and work with the FFT routine. I don't know.
If you want to experiment with it, I would just start and assume periodic boundary conditions and see if you get anything artificial, and then you can improve on it.
Yeah, I've noticed that people who have done hydrodynamical simulation of galaxies have used rather strange outer boundary condition, which allows a certain outflow of matter. And I don't understand exactly how it works, but
but those who do cosmological simulations use periodic boundary conditions.
I know.
And they form many galaxies in different places.
Yeah.
But then they also
have a big box.
Yeah.
It's not only one galaxy, they have a whole...
That's a cosmologic principle in some sense.
That's true.
Anyway, this last term, I think that would generate some problems if you want to keep that and just run the simulation that way. Because, for one thing, now we have gas falling onto the disk. It's not accreting the way you mean with accretion when you have an accretion disk. So then when the gas hits the disk, will it have the same velocity as the gas in the disk, or will it hit the disk with a sort of zero velocity? That's the question. In case you have the same velocity as the gas in the disk, then this term appears like this. If it's have a zero velocity, then the term disappears. But then again, you have maybe something strange happening regarding momentum conservation because you're increasing the density over time. That's one thing. And another thing is you might have something that looks a bit like a drag force if you have something in between those two extreme cases. And looking at the energy conservation...
this V is the gas velocity or the star velocity?
Oh yeah, V is the gas velocity, Vs is the stellar velocity, stellar component. So probably you have to separate these two components. Exactly how you're going to do that, I don't know. If you treat the stars as particles or you can treat the stars as a different kind of fluid or something. I'm not sure, but I think both would be doable, right, Bob?
I think so, yeah.
Anyway, the conservation of energy is also
If you
interesting.
treat them as particles, then of course you have to worry about how you treat the gravity. But that's what you're doing.
Yeah.
But We already have
But
part
the
of
self-gravity
it.
would be the same, I guess, right?
It's the same whether you have a 1 meter dust board or
You smooth it in some sense, or how do you
we
keep the
map
density?
we map onto a grid with a transversive cloud method, so that either you can do particle and silver, you can do a bit higher order. It basically means that the gravity on small scale is underestimated, but on large scales you get a very fine solution. So.
Well, the last term here is the last two terms, more or less. Has to do with supernovae. I mean, we have supernova explosions in this, which means you are sort of injecting energy into your gas by these explosions. So you will have some term including the what do you call it, kinetic energy.
What is heat at zero there?
Yeah, that's the coefficient that tells us how much of the supernova energy that is turned into kinetic energy, basically. So when the supernova goes off, you add some energy to the gas, basically, some kinetic energy, and that will, of course, affect the dynamics.
But we also have supernovae in the code, right?
Yeah, but this means normally, or at least to a large extent, thermal energy input as well.
Yeah.
Directly, not just by kinetics. Do you have that?
No, I haven't taken that into account
Plus gamma
yet,
term
because
we have.
sometimes people say that they have an effective coefficient where they sort of, I don't know exactly how that works, but I've seen what they've done previously in similar types of simulations, and they haven't treated the whole thing with the energy equation in detail, and they made approximations, and maybe we can do that better. I don't know.
I mean, I'm just
There
surprised.
will be some sort of cooling that
Mhm.
you heat up the gas, and then the gas would cool somehow, and there would be extra source terms again. That's as far as I can tell, but exactly how to formulate these source terms, I'm not certain. Maybe you can help me.
Already, so
Suggestions.
what normally people have done, and what we have done in our 99 paper is to have a delta function-like insertion of thermal energy locally.
Yeah.
So that would be a plus rho times gamma term in the last equation. And then you still have the gamma cool, a lambda cool term.
Yeah.
And we omitted kinetic terms,
Okay.
mostly.
And you find that to work
Technically, it
satisfactory way,
has
or-
a number of difficulties, but
Yeah. Okay. Well, I'm not. I mean, I don't think anyone knows exactly what.
I'm not sure why this should be any better. I mean, supernova problems are just very hard because you have
Yeah.
very high temperature gradients that contrast.
I think that's what people are guessing, and
Yeah.
You
Go
can use
up
some
all the way
clutch
up to
factors and
9
whatever.
Kelvin and down to 100 Kelvin, of course. Many orders of magnitude in temperature alone, and even more in pressure and density.
so here you see some of the problems you might encounter in trying to evolve the galaxy in terms of hydrodynamics. Well, I was hinting at some simplifications that can be made. I was saying instantaneous recycling for one thing. I mean, we're not interested in taking into account the exact delays depending on if we have long-lived low mass stars or the short-lived high mass stars. We just want to take into account that some of the gas is being effectively consumed over time by star formation. So maybe instantaneous recycling would do pretty well in order just to see how the gas flows are evolving in the galaxy. Maybe you can assume that then this 2D simulation might be sufficient to constrain the large-scale dynamics, even though, yes, on the local scale it would be completely wrong. Then if you have the too shallow galactic potential, you have another problem which we'll mention with galactic winds, of course, because then you would blow away gas from the disk, which is impossible if it's 2D disk.
So you will always blow away the gas. Only thing it will come back if the potential well is too strong. So, I mean, you will always get a thickened halo once you put a lot of energy from the supernova.
I agree. That's a problem, but at the same time, really, it's very costly.
Yeah, I understand.
It's a trade-off.
Actually, if you have self-gravity and a thin disk, you will also start getting non-axisymmetric instabilities.
Yeah.
And that may be something you want to have.
In a sense, yes. But I mean, you still want it to be sort of physical, and not
Yeah, I think
artificial due to boundary conditions.
physical non-axisymmetric gravitational instability, because which will make spirals.
Another simplification which is quite reasonable, I guess, is to assume that you have static dark halo. So you just add a static potential component for the dark halo, and then we don't have to think more about that. And another thing is to assume that the supernova explosion doesn't affect the large scale flows that much, so you can make these fuzzy approximations that I was mentioning that people are doing. Maybe that's another thing one can use to sort of simplify things. But then you have a problem with galactic winds. Of course, it still remains. How to treat that. Then, if we look at what has been done, I mean, there are a few simulations of this similar kinds that have been done, and I don't know, there was someone talking yesterday, I wasn't here, but yeah, it was you. I don't know exactly what you were saying yesterday, but what you were trying to simulate bar-driven flows, and you were simulating bar-driven flows as they're happening right now in a sense.
Right now?
Yeah, I mean, you see, try to observe, you can find signs of bar-driven gas flows in existing galaxies. And
connect separate diagnostic.
And that's what you were trying to do,
Yes.
basically. So, and there have been some attempts to look at the evolution of things also, but mainly people seem to end up with something of a stationary situation after a while. And then there are these sort of approximate mean profiles of the velocity field that they arrive at. And you get different results depending on what you assume about the baryonic density of the disk and what you assume about sound speed or all sorts of things. So those are the things one had to experiment with. Now, I think this stationary thing...
What are those plots?
Yeah, those plots are from this article, how to pronounce this out, from 2003, and that's the most recent simulation I found of that kind, that particular kind. I haven't looked deeply into the literature, but
So what one is showing?
yeah, that's right. What you have here is the mean velocity field as a function of radius. So this is sort of the radial gas flows. So you have an inflow here and you have an outflow here. And for different types of runs. And then you have the corresponding density profiles, which are more or less exponential one. Now, in these simulations, they have used these weird boundary conditions, and I think boundary conditions is the big issue here, how to treat boundaries. They were explaining in this article what he did with the boundaries, completely just explaining it in words. And I didn't understand a thing of it, to be honest. There was no equations at all, and that's just silly to me. And they came to the conclusion that this whole thing implies a sort of a steady state for the average flow, which is sort of strange. And after all, if you have this infall, as I was mentioning, you will definitely not have a steady state over a longer time scale. Things will change, basically. And then in this case, they used the closed box model, so you weren't an infall. But if you look at what the results they get for, I mean, this is not very representative, perhaps, but different baryonic densities leads to very different results. And since the baryonic density will increase over time, if we assume that the galaxy is on by a slow infall, then you will have some sort of evolution in the radial gas flows as well.
What is on the left and what on the right?
Let's see. This.
Yeah, that's why.
Yeah. I'm sorry, it's hard to see. I think I can't read what it says. I think this is gas, and this might be the stellar component or something. Probably, yes.
So that is
Both are density.
Density.
a log density here.
Yeah, it's a log density.
Yeah, there also it says log density.
Yeah, exactly. And then they have X and Y.
But here, you know, like it's from 5 until 8, right? And here from 6 until...
But I think it's different components, probably.
Yeah, it's different components, probably different scales as well. And then you have for the 20% disk, means that you have the 20% of the mass is due to the disk. And then you have 44, and you have 60, and so on, so increasing the baryonic density and the now, in the last case, you have pure disk, which is of course nonsense. So then,
Nonsense? Why is nonsense?
well, okay, you have to add something at least in order to get the right type of dynamics for all this, with the right rotation curve. Something has to be added, whether it's a dark halo or what it is, I don't care, but you have to add something. Okay. What Pencil must be able to do then, if we're going to run the whole thing as one simulation, you have to evolve over something like a Hubble time. I don't know if that's doable.
Yes, it is doable.
Yeah, I think we made some calculations and came to put it in 2D without magnetic fields and all those things. Maybe it's doable.
So you have to relate the sound quotient time over 1 point to the Hubble time.
You will have to add extra source terms in any case. That's the only way to do that. So infall might be a problem, but you have to add star formation and gas return in some sort of sense. You have to have self-gravity because the potential of stars and gas is significant in the disk. And perhaps we want to even check this in cylindrical coordinates, and if that's now working, as we heard earlier, that's great, because cylindrical coordinates are of course better when you're looking into the central parts, and that's where it's at the center where the party is basically in the galaxy, and it makes all sense because you usually find a bar at the center of the galaxy. So.
Why is cylindrical coordinate better? No, because imagine that
depending on
it's worse.
The resolution thing, basically.
I think will be a big problem from the inner boundary. There will be a lot of noise, so
that could be
one
also.
must be very careful.
But
that's why we use Cartesian grid to avoid the inner boundary problem.
So you don't need to specify a certain inner boundary condition. Like
No,
this.
no,
that's not true.
No, that's the advantage of using Cartesian grid.
You have then more noise in we can see cylindrical, right? Where
You mean outer boundary condition?
yeah.
I have tested the equilibrium state very carefully. The noise is very small, less than 5%, or even 3%. So I'm pretty sure the noise generated from the outside is very small.
But which
But the caveat is that the perturbation cannot be strong toward the outer boundary. If you have a strong perturbation around outer boundary, there can also be a lot of noise there.
Yeah, I think that's why they have these weird boundary conditions usually.
So people usually do is to create a lot of ghost zones to absorb those noise.
Yeah.
But I think that's kind of ad hoc. Need to be checked carefully.
Yeah, I mean, you mean you run into the same problem if you use the coordinates?
Yes.
Yeah.
Those are the same problem. Yeah.
Cartesian is perhaps better to...
Depends on what your model is.
Yeah.
I think in this case you may get away using condition grid, but you lose the resolution inside.
Yeah, I was afraid of that. I mean,
Yeah.
there's happening a lot of things in the center of the galaxy.
That's right. That's right.
So,
But you need to make a balance.
but if you make the grid dense enough, then it shouldn't be a problem. But then again, this.
But for 2D calculation, it's very cheap, so you can easily go as high as 4096 square without
Okay.
problem.
Yeah,
So I think that's good enough for your resolution.
Okay.
How do you see more noise while in the outer disk or in the inner disk?
I'm sorry?
You see more noise in the outer disk or in the inner disk?
You mean in what coordinate calculation? What in what calculation? In cylindrical. More noise from the inner.
Yeah, I guess it is in both ends.
Makes sense then, okay.
Yeah, and then just a few things. So if one can make this work, you can perhaps include the nucleus in this project to kind of go make extra subroutines with, because you can evolve the whole thing within the same code. You can probably compute the distribution of metals in the disk and so on. And using discrete supernova events and the mixing of the new elements in the ISM would be kind of interesting, which is something that has been done for like a local box or something, but going to larger scales. Going to larger scales would be interesting. And then again, this thing with baryonic infall and how to make that realistic, I don't know really how to do that. One thing one can do right away, I think, is something that we tried when we were trying to compute the also model the origin of what is known as detached shells around the AGB stars. I don't know how many of you know about this, but what we did was that we tried to compute what's happening on one scale using our model for the wind of an AGB star, and then following an evolutionary track for that star and sample points along the evolutionary track and compute models like that. And maybe you can do, then you get some time-dependent boundary condition for the computation of the evolution of the shell that forms around the star. What one perhaps could do is one can look at the expected evolution of a galaxy and make sample points and then compute models without closed box models, and then change the baryonic composition and make a grid of models and try to estimate how things would possibly evolve over time after that. I don't know, one way to get around it. So that's all.
Certainly a very ambitious plan.
Yeah, I guess.
This thing about baryonic reform, I mean, the way people have looked at it is to assume, let's say, a hot gas,
Yeah,
and then you have a cooling radius,
yeah.
and then you don't need to prescribe anything external. You just populate your halo with some density profile for the hot gas and let it fall in
the disk, yeah.
into the disk to make the disk by just conserving angular
Exactly what I
momentum.
meant by realistic modeling, but then again, we don't know if that's
Of course, what has also happened is that the way in which one thinks about the baryonic infra has changed, because the cosmological simulations show that there are two modes,
Yeah.
and there is this things just coming along, filaments, and directly inside, deep into the galaxy, and then there are things which are shot far away and then falling in slowly. So you may be okay doing whatever you want.
maybe. Yeah.
I want to make a comment about the Schmidt law.
Yeah.
I think that relationship is concerning the whole disk, not local. So,
Yeah, that's
so
true.
I think you are going to do local star formation. So
Yes.
the description may be very different from the Schmidt law.
The thing is, I don't think anyone knows exactly what a local star
I-
formation law would look like. So it's a sort of thing that you use. You guess that it is something similar even locally. But
I think Mordecai and I are trying to look into local analysis,
You
but
haven't-
we haven't had any definite answer yet.
Yeah.
But we are looking into that because we just analyzed in detail the large Magellan cloud about the gravitational instability and star formation. We found a very good correlation, but we are still trying to figure out what's this global analysis related with the local analysis, because we have a very detailed map of the galaxy, and we are looking into that possibility. But
What do you
still
find?
work going on. What?
So what do you find?
Basically, we just combine stellar contribution to the gravity with gas contribution. In the previous work, for example, from the chemicals, they all look into the gas density only, and you try to using the empirical correction factor to it. But now we explicitly formulate the stellar contribution to the gravity and make two-component model and try to find the gravitational instability and the star formation. We found that with this formalism, we can better describe and predict the location of the star formation site. So we think we are going into the right way, but that's still work going on in progress.
Okay, will that in the end lead to some sort of a new prescription for
Yes,
star
yes.
formation? Like
But
you-
I'm talking about the kiloparsec scale star formation. That may be related in your scale.
Yeah.
We are talking about star formation kiloparsec, and not the whole disk anymore. We are looking into the disk, more or less local.
You would naturally expect that sort of the potential of the galaxy would come into.
Yeah, I think both gas and stars play the role into the description. So the simple gas density threshold is too crude.
Yeah.
But I'm not sure about this, because maybe it's okay because larger uncertainties already screwed things up. So maybe simple density threshold is good enough. But I'm not sure. Just
I'm not
Just
sure.
get-
It's just first thing you pick up is the good old Schmidt law.
Any more questions? Comments?
Yes, I do. How realistic is it to treat the stars, you know, like yeah.
Quite, I would say. I mean,
Because
the mean free path is such that you can probably call it approximate it as food.
Depends on the scale.
I mean, it has on a scale, probably a large scale.
If you're looking at
Yeah.
I would guess it would be.
Exactly.
But the problem would be that it's collisionless. So
So
you
it means
need
it
to,
is pressureless then, sort of.
it won't be pressureless because you have velocity dispersion.
Yeah.
So
But this is something the
you
code,
need to close
No,
this
it
equation
doesn't
somehow.
but this is something the code can handle. With
So you-
particles. So these stars are basically big dust particles, right?
So instead of treating it as fluid, you treat, if you can solve the Boltzmann equation, or sorry, even the Vlasov equation, that's what you need to do.
Let's see that.
But our approach to solving the Boltzmann equation would be to have superparticles
Fine,
moving
Yeah.
on the grid and then have a particle mesh interaction.
yes.
With the gas. I think
Yeah.
this would be fine also.
Maybe that's not so bad.
yeah,
I think it is. Yeah, I think it's fine.
but yeah, no, like if he uses then particle away, then how to make more, right? Because these stars.
Gas turns into stars.
Yeah, exactly.
This you can do, because you can say each particle, you can make a more advanced problem, you can say each single universal particle represents a number of actual stars, or a mass, a total mass of actual stars, and then you can make some way to increase or decrease that number.
I think that's the way people have done this before. They define what they call superstars, which are
right.
ranging between one stellar mass and 10,000 stellar masses, and you have some average stellar mass.
That also means when you do the gravity and you map onto a grid, one particle is not 1.
Yeah,
One particle is 0.1 and the other particle is 100.
So we can still keep the number of the particles there, constant then, and we can then have. Okay.
The mass will keep on increasing with time.
Yes,
Alright.
or decreasing.
Or decreasing.
No.
Of course, in SPH, they have the same particle representing both gas stars,
Yeah.
hot gas, cold gas.
Yeah. A dark matter. Any more questions? So let's take my time. And I suggest we make a break now until 4:30. This is fine, right? We can break until 4:30. There's only one more talk today. It's
now it's
3:40 now.
Now it's 3:30. But,
No, it's just 3:40. So I suggest we take a longer break now until 4:30.